Alright, let's do this exercise. This is really cool because this uses a lot of basic point set topology, and this stuff is very visual. So I like being able to do this, and especially I'm going to sort of kick this off with a visual demonstration of the first part of this proof. So, we want to prove that E prime is closed. We have defined sets in this textbook to be sets which contain all of their limit points. That's not the most general definition. The more general definition is that closed sets are defined to be complements of open sets. And if you define closed sets to be complements of open sets, then you can prove later on, not too much later on, but a little bit later on, you can prove as a theorem that all closed sets under this definition contain their limit points. So this isn't necessarily the cleanest introduction to open and closed sets, but this works fine. So anyways, we want to prove that E prime is closed, and so it suffices to prove that E prime contains all its limit points. Now the limit points of E prime, that's going to be E prime prime. Because remember, E prime is the set of limit points of E, so E prime prime is the set of limit points of E prime. We want to prove that E prime contains its limit points, so we want to prove that E prime contains E. And so let me draw a picture of the proof and prove this visually. And then after doing that, we will prove this rigorously using symbols. But if you understand the picture that I'm about to draw, then that should be enough. Okay, so we want to prove that E double prime is in E prime. So let's take any element of E double prime. Now, then X is a limit point of E prime, which means that if you choose any neighborhood of X, let's call it U. So U is a neighborhood of X. Remember, neighborhoods of points are open balls containing that point. So it's a set of points that are at most a set distance away. So here you can think of this as a circle, and this would be the radius R. And so this set U contains all points whose distance from X is at most R. So anyways, the fact that X is a limit point of E prime guarantees that for any neighborhood U, we can choose an element, let's call it Y, which is not equal to X and is in this neighborhood U, but is also in E prime. Okay? So now, what we're going to do is, let's see here, I didn't draw this big enough. Am I able to stretch this? Here, no. Here, let me try doing this. I'm going to try to stretch this. Can I do this? Nice. Okay. And by the way, I will use these dotted lines to refer to open sets. Because you see these dotted lines, it sort of represents the boundary of the open set, and remember, open sets do not contain their boundary. So this dotted set sort of shows you where the open set ends. Anyways, so now Y is in E prime. So E prime is a limit point of E. So if we choose any neighborhood of Y, this neighborhood will contain an element of E, which is not Y. And that's what we want to use. So now what we're going to do is we want to choose our neighborhood wisely, though, because we want to end up with something in U. So note that U is an open neighborhood of Y, and if we take U and remove the point X, then what we're doing is you're taking an open set, namely U, and you're removing a closed set, namely the set containing the element X. And if you take an open set and remove a closed set, you're left with an open set. I'll go into more detail on that specific detail later, if it's not clear. But anyways, So if you take U and remove the point X, then you get an open neighborhood. Then you get an open set. Okay, so yeah, open neighborhoods are balls. So the open set U set minus X, the set U with the point X removed. This is an open set which contains Y. It's not technically an open neighborhood of Y, but it is an open set which contains Y. And we know that open sets are, any element of an open set is contained in the interior of the open set, which means that there is an open neighborhood of that point which is contained within this open set. I.e., there isn't, and you can see this visually, there is an open ball we can draw here, let's call it V, which is an open neighborhood of Y and is entirely contained in the set U with the point X removed. So anyways, this is V. Sort of pretend that this element Y here is in the middle of V. Here, I'll actually draw it like this, so that it's more obvious that this is the point Y is the center of the open ball V. So anyways, Y is an element of E prime, so Y is a limit point of E, which means that for every single neighborhood of Y, there is an element, we'll call it Z, which is an element of V which is not Y, but which is contained in E. Okay? So now what have we done? Now we found this element Z, and what does this element Z tell us? This element Z is an element of the set E, which is contained in the open neighborhood U of X, and is also not equal to X. And remember, that's what we need to prove that an element is contained in E prime. So the fact that such an element Z exists tells us that X is not just contained in E prime prime, but X is actually contained in E prime. And since this holds for every element X in E prime prime, we can conclude that E prime prime is contained in E prime. And that finishes the proof. If you were able to follow everything that I said and you understand the picture, then there isn't really anything else that is necessary for this proof. However, if you're writing this up on like a homework assignment, you don't have the luxury of being able to draw a picture and explain the picture to your teacher or to the grader. And so what we have to do is actually write out a proof. So let's go through this entire thing that I just did, but now we'll do it using words. Okay, so it suffices to prove E prime prime is contained in E prime. Okay, so let X be contained in E prime prime. Then for any neighborhood or open neighborhood, it doesn't matter. Some textbooks do make a distinction, but in this textbook, we'll just assume that they're both the same and it doesn't matter. Then for every neighborhood U of X, and the way I'm going to write this is, there is an element Y contained in the open neighborhood, and this element Y is not equal to X, so I'll just write that as Y is an element of U set minus X, and Y is also an element of E prime. So I'll write that as Y is contained in U set minus X intersect with E prime. If you sort of break apart this notation, this is exactly what it means. This is exactly the type of element that you require for the definition of a limit point. Okay, so note that so U set minus X, well, this is the same as U intersected with the set of the complement of the set containing only the element X. So this is an intersection of open sets and thus is open. Furthermore, it's not empty because X is the point X is contained in, because U is a neighborhood, it contains points besides X, and so you remove x is going to be non-empty, but that's not super important. At least not here. Like, it's not something you have to worry about. Okay, so this is an intersection of open sets and thus is open. Okay. Since y is contained in U set remove x, y is in the interior of U set minus x, because U set minus x is open. This means that there is a neighborhood V of y in U set minus x. Or, in other words, y is an element of V, and V is entirely contained in U set minus x. And of course, V can be written as a ball of some set radius about y, i.e. V consists of all points which are at most a set distance away from y. Okay. Now, since y is in E prime, and since V is a neighborhood of y, we know by the definition of V prime that there is some element, let's call it z, which is so it's in V and it's not equal to y, but it's also in E. Now, since z is since V set minus y, well, this is obviously an element of V, which is contained in U set minus x. We have z is in, V set minus y is contained in U set minus x, so we can replace this first part here with U set minus x intersected with E. Okay, so for every x in E double prime, so for every neighborhood U of this element x in E double prime, there exists an element z which is contained in U set minus x and also contained in E. The existence of such a z for each neighborhood U is equivalent to the statement or the fact that x is in E prime. So we took just any arbitrary element x in E double prime and proved that x is in E prime. This holds for any x in E double prime, and thus E double prime is contained in E prime, and hence E prime is closed. Okay. So there we go. That finishes the first part of this problem. So now let's move on. Next, we must prove E prime is equal to E closure prime. So the limit points of E are also the limit points of E closure. Let's see here. What is E closure? E closure is E, and you take the union of E with the limit points of E, and so clearly, since this holds, we have E is contained in E closure, because E is contained in E union E closure, which is obviously which is equal to E closure. Yeah, E is contained in E closure. Any limit, see here, if A is contained in B, then any limit point of A is a limit point of B, and thus we have E contained in E closure implies that E prime is contained in E closure prime. Now, I guess you might want to include a proof that any limit point of A is a limit point of B if A is contained in B, but it's pretty straightforward, because if you go back to the definition of being a limit point, then you need the existence of like such an element like Z, which is in U set minus X, and in E. So here you have Z is a limit point of A if, no, X is a limit point of A if for every neighborhood U of X, there is an element Z which is in U set minus X and also in A. But A is contained in B, and so for every neighborhood of X, Z is contained in U set minus X intersected with B as well, because A is contained in B, so the intersections are contained in each other. And so, yeah, which means that that point that you've chosen is actually a limit point of B, and this holds for every limit point of A, and hence the limit points of A are all limit points of A are limit points of B. You can write that out if you want. I think it's clear enough that it's not necessary to write out, but I mean, different people and different professors have different preferences on how much detail you go into. But anyways, we have this. Alright. To prove, now we want to prove that E prime equals E closure prime. So the next thing we're going to want to prove is E closure prime is contained in E prime. Because if E prime is contained in E closure prime and E closure prime is contained in E prime, then E prime equals E closure prime. This is how you want to go about proving equality of sets. You want to prove that each set is contained in the other. So to prove the other one, this is going to require a little bit of work. Now, when I was going through the proof of this, I was going through and I was like, wow, you could prove this in a way that's very similar to the first part of this exercise where we prove that E prime prime is contained in E prime. And usually, if you're proving something in the same way twice, that you should sort of have a gut feeling that you're not doing things as efficiently as you could be. Because the point of math is to do something once and then generalize so that you don't have to do it again. So that in the future you can just refer to that thing that you did once. So I was going through it the second time and I was like, wow, I should be able to... The fact that this proof is very similar to the first proof, I should be able to use the result of the first part in proving this. And it turns out you can do that. There is one other thing that you need to do, which might make it take a little longer potentially, but it also helps you learn more things about limit points. So here's what we need to prove. We must show that for any two sets A and B, the set of limit points of A union B is contained in limit points of A union limit points of B. And in fact, you have equality here because obviously any limit point of A is a limit point of A union B, and any limit point of B is a limit point of A union B. But the other direction is the one that we need to use, and it's also the one that actually is tricky to prove. And in fact, this doesn't work for just the union of two sets. It works for finite unions. But if you're interested in that, I'll leave that to you. You should be able to see how to prove that if you want, based on how this proof goes. Okay. So let X be an element of A union B prime. We want to show that X is an A prime union B prime, or that X is either an A prime or an B prime. Okay, so let X be in the let X be a limit point of this union. For each natural number n, there exists an element xn, which is contained in the ball of radius 1 over n centered at x, and is also contained in well, here I want to write this in a way that makes it look like what I had before. So it's in a ball of radius 1 over n over x, but it also is not equal to x. And it's also in the set A union B. And the reason that such a, and of course n is not in this natural numbers here because I'm an analyst. I don't allow these to, this doesn't include the number 0. Okay, so there's an xn. So b 1 over nx, this is a neighborhood of x. And so because it's a neighborhood of x, and because x is a limit point of A union B, there is such an element xn here. Okay, so for each n and n, since xn is in A union B, then xn is going to be in A, or xn is going to be in B. It could be in both. A and B could intersect, and it could be in both of them, but it has to be in one of them. Now let I be the set of indices, lowercase I, such that xi is in A, and j be the set of indices j and n, such that xj is in B. Now, I union j is going to be equal to the set of natural numbers, because obviously I and j are both subsets of the natural numbers, and so I union j is going to be contained in the set of natural numbers, but every single xn is contained in either A or B, or possibly both, which means that n is going to be entirely contained in I union j. So therefore these two sets are equal. Okay, and since these two sets are equal, and since n is infinite, I union j is infinite. And so either I so I union j is infinite, which means that I or j is infinite. If these were both finite, then their union would be finite, and thus it could not equal all of the natural numbers. Therefore, either I or j is infinite, possibly both. Okay, so if I is infinite, then xi, I and I, is a subset of A, which converges to x. And why does it converge to x? It converges to x because these balls have radius 1 over n. which means that as you go further on in the sequence, you get closer and closer and closer to x. And so, if you give me any epsilon, if I choose n such that n is greater than 1 over epsilon, then xn is going to be in the ball of radius 1 over n, centered at x, which is contained in the ball of radius epsilon, centered at x, which means that xn is within epsilon of x. And the fact that you can choose such an xn for every single epsilon implies that the xn's converge to x. Okay, so if I is infinite, then this is a subset of A which converges to x. And so x, therefore, is a limit point of A because A contains a sequence which converges to x. That's an equivalent condition for being a limit point. So x is in A prime, and of course A prime is contained in A prime union B prime. If J is infinite, then by a very similar argument, the set of elements of the form xj where j is in J, it's a I shouldn't say it's a sequence, an infinite sequence in A, which converges to x, and so x is a limit point of A, which is contained in the union of limit points of A and B. If J is infinite, then the set of points of the form xj where j is in capital J, this is an infinite sequence in B which converges to x, and so x is contained in B prime, which is then contained in A prime union B prime. So we are guaranteed to have x is in A prime union B prime, and thus A union B prime is contained in A prime union B prime. Using this fact, okay, so that's the thing that we wanted to prove. Using this fact with the fact that E double prime is contained in E prime, remember, that's what we proved in the first part of this exercise. So now what do we have? We have E closure prime is equal to, well, E closure is E union E prime. So it's E union E prime prime. And using A equals E and B equals E prime, this is contained in E prime union E prime prime. But E prime prime is contained in E prime, and so this is contained in E prime union E prime. But if you take any set and take its union with itself, you get itself. And so E closure prime is contained in E prime. And thus, hence, we now have E closure prime is contained in E prime, and combining that with E prime is contained in E closure prime, we have E closure prime is equal to E prime. Okay, so finally, to prove E and, wait, what is it? Is it E and E prime? E prime and E double prime need not be equal. Let E be the set of points of the form 1 over n, where n is a natural number. We know from a previous exercise that E prime is equal to, well, E prime contains just the number 0. And so E double prime, well, this is just limit points of the set containing just one element. But if you have a set containing one element, then since there's only one element in there, you can't satisfy the limit point condition. And so the set of limit points of this set is the empty set. And clearly this is not equal to the set containing just 0, which is E prime. Okay, so we have proven that E prime and E double prime need not be equal. Of course, there are situations where you have them being equal, like consider a E is a ball of radius 1 centered at 0, then E prime equals E prime prime, because if you think about it, the set of, yes. Okay, so the ball of radius 1 centered at 0, the set of limit points of this, well, anything inside the ball is a limit point, but also anything on the boundary is also a limit point. So E prime is actually equal to B1, 0 closure, and then the limit points of E prime prime, well, this is just going to be the closure of the closure, which is going to be B1, 0, so it's going to be the same thing. So you do have plenty of instances in which E1, here, let me get rid of it. You do have plenty of instances in which E1, E prime and E double prime are the same thing, but there are also plenty of cases in which they aren't, particularly cases on the real line, and this is one example of it. Yeah, this problem did not specify that things were taking place in R2. It said things, it just didn't specify the spaces, and so you can consider examples in R. And so here's an example on the real line where E prime and E double prime are not equal. And that finishes our proof.